Every drivetrain system explained. Front-wheel drive, FWD. Front-wheel drive puts the engine, transmission, and differential all in one compact unit at the front of your car. The engine sits sideways, what engineers call transverse mounting. Power flows directly from the engine through the transmission to the front wheels via two half shafts. No drive shaft needed, no tunnel through the cabin. Here's what makes FWD revolutionary. It uses 30% fewer parts than rear-wheel drive. The 1959 Mini pioneered this layout by turning the engine sideways and mounting the transmission underneath in the oil pan. This freed up 80% of the car's space for passengers. Today, 70% of all cars use this layout, including the Honda Civic, Toyota Camry, and Volkswagen Golf. The cost advantage is significant. FWD systems cost manufacturers $1,500 to $2,000 less to produce than RWD. That savings gets passed to buyers. A base Civic costs $25,000, while a comparable RWD BMW 2 Series starts at $37,000. You're paying $12,000 extra, partly for the drivetrain configuration. The physics work against performance. With 60 to 65% of weight over the front wheels, those same wheels must handle steering, acceleration, and braking simultaneously. Under hard acceleration, weight transfers backward, reducing front tire grip exactly when you need it most. Torque steer becomes problematic above 250 horsepower. When you accelerate hard, unequal length drive shafts create different forces that pull the steering wheel sideways. The Honda Civic Type R needs sophisticated dual-axis, a strut suspension, just to manage 306 horsepower. The old Mazda Speed 3 with 263 horsepower would change lanes under acceleration without steering input. FWD works brilliantly for economy cars, but reaches its limit around 300 to 350 horsepower. Beyond that, the physics become unmanageable. The Focus RS needed AWD to handle 350 horsepower effectively. Rear-wheel drive, RWD. Rear-wheel drive separates responsibilities. Front wheels steer, rear wheels accelerate. The engine sits longitudinally, sending power through the transmission, down a drive shaft running under the car, through a differential that splits power to both rear wheels. Watch this cutaway. The drive shaft spins at thousands of RPM, transferring power 4 to 6 feet from the transmission to the rear differential. The differential allows wheels to rotate at different speeds while cornering. The outside wheel travels farther and needs to spin faster than the inside wheel. This layout enables near-perfect 50-50 weight distribution. BMW obsesses over this, relocating batteries to the trunk and mounting engines behind the front axle line. The M3 achieves 50.1/49.9 distribution. This balance creates neutral handling, where the car responds predictably to inputs. Physics helps during acceleration. When you accelerate, weight transfers to the rear wheels, increasing traction exactly when you need it. A Dodge Challenger Hellcat can put 707 horsepower through rear wheels, only because physics assists grip. The same power through front wheels would just create tire smoke. RWD enables controlled oversteer, when rear wheels lose traction and slide sideways. While this sounds dangerous, it's predictable. Apply opposite steering lock, modulate throttle, and you're drifting. Every Formula Drift car uses RWD because this characteristic is impossible with FWD. The mechanical separation means each component operates optimally. Front suspension can be tuned purely for steering feel without compromising for drive shafts. Rear suspension focuses solely on putting power down. This specialization is why sports cars from the Mazda MX-5 to Ferrari 812 use RWD. The drive shaft tunnel consumes interior space. That hump running through your car's center is the drive shaft housing. RWD sedans typically have 2 to 3 inches less rear legroom than FWD equivalents. The BMW 3 Series has less rear space than the smaller FWD Audi A3. Cost and complexity increase significantly. The drive shaft, differential, and additional universal joints add $1,500 to $2,000 to manufacturing costs. RWD cars typically weigh 150 to 200 pounds more than FWD equivalents. Poor weather traction without weight over drive wheels makes RWD challenging in snow. All-wheel drive, AWD. All-wheel drive sends power to all 4 wheels through a center differential or coupling that splits torque between front and rear axles. Modern systems use electronic control to vary power distribution based on conditions. 3 components make AWD possible: the center differential that splits power, the transfer case that sends it front and rear, and electronic controls that manage distribution. The center diff is crucial. It allows front and rear axles to rotate at different speeds while cornering. Subaru's symmetrical AWD uses a longitudinal engine with a mechanical center. Differential sending power 50-50 continuously. Audi's Quattro uses a torsion differential that can vary power 40-60 to 60-40 based on grip. BMW's xDrive can send 100% to either axle in milliseconds. Full-time AWD, like Subaru's system, always powers all wheels. The WRX STI uses 3 differentials: front, center, and rear, with the center diff adjustable from 35-65 to 50-50 split. This provides predictable handling in all conditions. Part-time AWD, like Honda's, real-time AWD primarily drives front wheels, engaging rear wheels when slip is detected. This saves fuel but provides less predictable handling. The CR-V only sends 30% maximum to rear wheels. Performance AWD systems are different entirely. The Nissan GT-R's Atessa ETS monitors conditions 1,000 times per second, predictively sending power where needed before slip occurs. It can transfer 100% to front wheels in 0.01 seconds. The system helped the GT-R achieve 2.7 second 0 to 60 times, despite weighing 3,800 pounds. Weight and complexity are significant. AWD adds 150 to 300 pounds versus FWD/RWD. The Audi S4's Quattro system adds 200 pounds over a theoretical RWD version. You're carrying an extra passenger everywhere. Fuel economy suffers by 2 to 3 miles per gallon city, 1 to 2 miles per gallon highway. Over 100,000 miles, that's $3,000 to $5,000 in extra fuel costs. Maintenance increases, with transfer case fluid changes every 30,000 to 50,000 miles, at $150 to $300 each. Four-wheel drive, 4WD. Four-wheel drive uses a transfer case to mechanically lock front and rear axles together. Unlike AWD's variable power distribution, 4WD forces both axles to rotate identically. This provides maximum traction off-road, but can damage components on pavement. The transfer case contains gears that can disconnect the front axle, 2-wheel drive mode, or lock it to the rear axle, 4-wheel drive mode. Low-range gearing multiplies torque 2.5 to 4 times. A Jeep Wrangler. Rubicon in 4-low creates an 84-to-1 crawl ratio, enough torque to climb near vertical obstacles at 0.5 miles per hour. The system is mechanically simple and robust. The 1941 Willys Jeep created the template still used today: engine to transmission, to transfer case to solid axles. The Toyota Land Cruiser 70 Series uses essentially identical architecture because it works reliably in extreme conditions. Standard open differentials allow wheels to spin at different speeds, but send power to the wheel with least resistance. One wheel in mud means 0 forward progress. Locking differentials force both wheels on an axle to rotate together, maintaining traction even with one wheel airborne. The Jeep Wrangler Rubicon has electronic locking differentials front and rear. Engage them and it can climb obstacles with only 2 wheels touching ground. One front, one rear. The Mercedes G-Class has 3 locking diffs, making it nearly unstoppable off-road. Manual locking hubs on older trucks physically connect and disconnect front wheels from the axle. You must exit the vehicle and turn the hubs by hand. Electronic locking, like Ford's system, engages from inside, but adds complexity and potential failure points. Driving in 4-wheel drive on pavement causes driveline binding. Since all wheels are forced to rotate identically but travel different distances when turning, massive stress builds in the drivetrain. This causes crow hop. The vehicle literally jumps sideways to relieve stress. Extended pavement driving in 4-wheel drive destroys tires, U-joints, and transfer cases. The repair bill can exceed $5,000. This is why 4-wheel drive is only for low-speed, low-traction situations. Above 25 miles per hour on pavement, you must use 2-wheel drive. 6x6. 6-wheel drive adds a third axle for extreme capability. The Mercedes G63 AMG 6x6 started as an Australian military vehicle before becoming a $500,000 civilian truck. Power splits through 2 transfer cases to 3 differentials, 1 per axle. The engineering is complex, but the capability is unmatched. With 6 contact patches and 37-inch tires, the G63 6x6 has 18 inches of ground clearance and can ford 3.3 feet of water. Portal axles, gearboxes at each wheel, lift the axles above wheel centers for additional clearance. Military 6x6 trucks like the M35 Deuce and a Half use simpler systems. The front axle engages for off-road while 2 rear axles stay permanently driven. These trucks carry 5,000-pound loads through terrain that stops any 4x4. The US military has used various 6x6 configurations since World War II. 8x8. Eight-wheel drive vehicles exist for extreme military and exploration use. The BTR-80 armored personnel carrier uses 8x8 to maintain mobility after mine damage. Lose 2 wheels and it keeps moving. The Avtoros Shaman is a civilian 8x8 that drives across lakes. Each wheel has independent suspension with massive low-pressure tires acting as flotation devices. The drivetrain uses mechanical differentials with selective locking, allowing turning despite 8 driven wheels. These systems use mechanical simplicity for reliability. Drive shafts run to each axle with power takeoffs at each differential. Turning requires selective braking or clutch packs to allow speed differences between wheels. The complexity comes from packaging 8 drive shafts and 4 differentials. Single motor systems. Single motor EVs place one motor driving either front or rear wheels through a reduction gear and differential. The base Tesla Model 3 uses a rear motor, producing 283 horsepower. No transmission needed, electric motors deliver usable power from 0 to 18,000 RPM. This simplicity means fewer parts to fail. A Model 3 drivetrain has about 20 moving parts versus 2,000 plus in a conventional automatic transmission car. Maintenance involves just reduction gear fluid changes every 100,000 miles. Dual motor AWD. Dual motor systems place one motor per axle with no mechanical connection between them. Tesla's Model S uses different size motors. A smaller front motor for efficiency and larger rear for performance. Software controls power distribution 1,000 times per second. The Model Y long range uses this layout for 384 horsepower combined. The computer can send 100% power to either axle instantly. In snow, it transfers power faster than mechanical AWD systems can react. Efficiency improves because each motor operates in its optimal range. Tri- and quad motor systems. The Model S Plaid uses 3 motors, 1 front, 2 rear. Each rear motor drives one wheel independently, enabling torque vectoring without mechanical differentials. This creates perfect cornering dynamics, applying more power to the outside wheel to rotate the car. Rivian's R1T quad motor system places one motor at each wheel. This enables tank turns, spinning in place by rotating one side forward and the other backward. Each wheel becomes independently controllable. The system produces 835 horsepower and 908 pound-feet of torque, while enabling capabilities impossible with mechanical drivetrains. Parallel hybrids. Parallel hybrids add electric motors to conventional drivetrains. The Honda Accord Hybrid places a motor between engine and transmission. Both power sources can drive wheels simultaneously or independently. The motor adds 181 horsepower to the engine's 143, totaling 204 combined. This system is mechanically simple but limited. The motor only assists acceleration and can't transform the driving experience. Fuel economy improves 15 to 20% in city driving, where the motor contributes most. Series hybrids. Series hybrids use engines solely as generators. The BMW i3 range extender's engine never drives wheels directly, it only charges the battery. The 38 horsepower engine maintains charge, while the 170 horsepower motor drives wheels. This allows optimal engine operation at constant RPM for maximum efficiency. The downside is requiring large batteries and motors, since the engine can't directly assist acceleration. Power split hybrids. Toyota's hybrid Synergy drive uses planetary gears to blend engine and motor power infinitely. The system can operate as series hybrid at low speeds, parallel at cruise, or pure electric when possible. The Prius achieves 54 miles per gallon city through this flexibility. The mechanical complexity is significant with planetary gear sets and 2 motor generators, but reliability is proven with many Prius taxis exceeding 300,000 miles on original components. Mid and rear engine RWD, mid-engine layout, places the engine between the axles, ahead of the rear wheels. Every modern supercar uses this for optimal weight distribution. The Chevrolet Corvette C8 moved to mid-engine after 67 years of front-engine design, improving lap times by 5 seconds. Rear-engine layout puts the engine behind the rear axle. Only Porsche 911 maintains this configuration. The rearward weight bias creates unique handling characteristics. Massive traction under acceleration, but tendency toward snap oversteer. Porsche spent 60 years engineering solutions, including rear-wheel steering and advanced stability control. Track and alternative systems. Tracked vehicles replace wheels, with continuous tracks for ultimate traction. The Ripsaw EV2 civilian tank achieves 60 miles per hour on tracks. No differentials needed. Tracks slip against ground to turn. Terrible efficiency on pavement, but unstoppable off-road. Portal axles add gearboxes at each wheel hub. The Mercedes G-Class 4x4 squared gains 6 inches of ground clearance without suspension lift. The Unimog uses them for 20-plus inches of clearance, driving over obstacles that would destroy conventional trucks. In-wheel motors put motors inside wheel hubs, eliminating all drivetrain components. Lordstown tried this with the Endurance pickup. Each wheel becomes independent with no mechanical connections. The problem is unsprung weight destroying ride quality, and motors getting damaged by impacts. Steer-by-wire eliminates mechanical steering connections. The Infiniti Q50 pioneered this with direct adaptive steering. Tesla's Cybertruck uses it too. No steering column means infinite adjustability and more crash protection space. The truth is, we're entering an era where mechanical limitations don't exist. Software defines capability. A single vehicle can transform from rock crawler to track car by changing code. The question isn't what's possible anymore, it's what's actually useful versus just showing off. Every drivetrain system exists because someone, somewhere, needs exactly what it offers. Even that ridiculous 6x6 Mercedes found 100 buyers willing to pay $500,000 for six-wheel drive they'll never use. Because at the end of the day, cars aren't just transportation. They're freedom, identity, and dreams made of metal. Every drivetrain system is someone's perfect answer to a question they might not even know they're asking. If you enjoyed this video, subscribe for more. See you in the next video.